after we've finished the differentiation or the derivatives and their applications. Today we will discuss the integration, which is an operator inverse in operation to the differentiation, to the differential operator. It's denoted by this stretched s along with the dx indicating with respect to x, and we will have the function in between both of them. We have two types of integration, definite and indefinite, that we will discuss. We will discuss also some integration rules, the general power rule, the natural exponential, and the natural logarithmic. So finding an integral is the reverse of finding a derivative. They are exactly opposite in operation, like when we need to get rid of 2 times x and we want to solve for x. What shall we do here? Let me show you what I mean. If we have, for example, 2 times x and we need equals 4 and we need to solve for x. So what do? We would divide both sides by 2, right? In order to solve x as 2. Now the integration is the opposite operation of derivative. So let's imagine that we're having x power 2 plus 4. This is the function. And we will apply this operator, the differential, get the derivative. What will be the derivative? We know that we drop the power and subtract 1, and the derivative of the constant is 0. So that's the derivative. This is the f dash, if this is called f. Now this operator is going to apply over the output, which is the derivative of a function, and with the rules we will get that this is equivalent to x power 2 plus c. So we will be able to get back to the x power 2 from the 2x using the rules, but the constant will always be kept as it is. So it's in general the opposite operation. We can also say that inside this operator we have the derivative of a function, and then we solve this operator, this stretched s and dx, in order to get the function before the derivative plus c. And we will discuss that c. Okay. So here is the same thing. We have the derivative of x squared plus c as 2x. And if we got 2x inside the integral, it will return to the x power 2 plus c, plus a constant. That's the notation that we have discussed. One of its definitions is being the antiderivative. One of the integration definitions is being an antiderivative. So applying this stretched s in green and the dx to the 2x, we will get x to the power of 2 plus c. In general, what happens? Let's discuss this. So here we said that using the rules, we will get back to the x power of 2. What do we do here? Actually, we are asked if we have a number inside this operator. Let's see two types of functions. If we have a number, any number a, this number a was the derivative of a times x plus c, such that a is a number. And then if we have any power of x, x to the power of n, this will be equal to x to the power of n plus 1 divided by the n plus 1. Okay, such that n is any number as well raised to the power of x. So based on these two rules, we were able to solve that one. So this integration here, if we have taken it here, we can take the 2 outside, because this integration is a linear operator as we discussed in the lecture. So we can take it out, and the integration of a constant times function is the same as the integration of the constant times the integration of the function. That's why we can take the constant out and then we apply the rule to the x. What do we do to the x? We would raise its power. What's the power of x here? It has no power, which means it's 1. So we will add 1 and divide and say plus c. And therefore, this 2 will go with that one. And we will be left with x power 2 plus c. That was the function at the beginning. We were able to retrieve the x squared, while the constant, we said that there were a constant. However, we will discuss that later about the constant. Let's get to our worksheet. And take part A. Solve. Now it's 3 to the square root of x. What can we do with this? We know that the equivalent power of the square root, like we did in the differentiation, we have a rule here for the power of x. So you will change that radical, or we will rewrite it as a fraction power. The 3 is a constant, so we can take it out, and then we will have the integration of x to the power of half dx. Now we will apply the rule where we add the power and divide with it. The new power is half plus 1, which is 3 over 2, divided by 3 over 2, plus the constant c. If we simplify these numbers, 3 divided 3 over 2, it's going to be 2 times x power 3 over 2 plus c, and that's it. Now if we want to verify this solution, although it's not required in the question, but let's do it once. To verify it means to prove that that is the function where this was its f dash, so that inside the integral we have a derivative and we were able to retrieve the function itself plus constant. Now let's try to differentiate that function that we got. We of course will drop the power and then subtract 1 from the power to return to its half. Okay, and we can simplify this out to get back to the 3 times x to the power of half, right? This 2 will go with the other one. So here we have returned, yes, that was the function inside the integral that we had here, right? Which act as the f dash for that f. So now we have verified the concept. Let's go with more confidence into the problems of the worksheet. Let's pick this function. So here we have the subtraction and addition of different elementary functions. We can rewrite them in order to be able to apply the rule. The rule is x should have a power. Here 2 is over x to the power of 3, so we can rewrite it as 2 times x to the power, yes, negative 3. We know that 1 over x power n is x to the power of negative n, and we can use it here. And then minus 5x to the power of 3, and then plus 4x dx. Now, of course, this minus and plus act as separators like we are used to. So what we see in our minds is that we have the integration of 2 times x to the power of negative 3 dx minus the integration of 5x power 3 dx plus the integration of 4x dx. Moreover, the constants can get outside the operator because it's a linear operator. So it will be like this. We can see it like that, and we don't have to write them separately, but we want to make sure that all of us see it like that. Very well. Now we are able to simply apply the integration rule to each power of x alone. So we have 2 is dropping, will drop, and x to the power of negative 3 plus 1, this is negative 2 divided the new power. And then minus 5 will drop, x will be to the power of 3 plus 1 and divide the new power, plus 4, and x will be to the power of plus 1 divided the new power, and finally plus c. We can simplify this out, yes, and we might leave it like we are used to if we are asked to apply the rule or apply the operator only. So we can just leave it like this, or we might simplify it to be of a better form. And this x to the power of negative 2, we can drop it to be 1 over x to the power of 2. We will combine the 5 over 4 and then plus 4 over 2, which is 2x squared plus c. Now it's time to discuss what about the c. Let's talk about the c, which is the integral constant. Imagine we have some functions like x power 2 plus pi and x power 2 minus e and x power 2 and x power 2 plus 100. And we need to find the derivative of all of these functions. So let's differentiate the first function. Of course, we will drop the power and subtract 1 plus the derivative of pi. Pi is 3.14, so it's a number and derivative is 0. Here the derivative as well is 2x, and derivative of e by itself is a number 2 point something, so its derivative is 0. And then the x squared alone, its derivative is 2x, and that one, its derivative is 2x. See now that all of these different functions, their derivative is the same function, 2x. Applying this operator, the derivative or the d by dx, let's apply the opposite. If we have the 2 to the times x, and we will apply this operator using the rule that we have just discussed, what we are going to do, we will say that the 2 is a constant, it will drop, and the integration of x, we will add 1 to the power and divide, and here we go then plus c, right, which can be simplified into x squared plus c. Yes, truly that was the functions, or better to say the family of functions that can generate this 2x as a derivative. So this 2x, which is the derivative of a function, actually it's the derivative of a family of functions. And we can describe this using that integration constant. X power 2 plus any constant. You remember that x, if we have x to the power of 2, we will have a graph of a u shape or the parabola, which will look like this. And if we have x power 2 plus constant, this means that the u shape is shifted vertically upwards. If this is x power 2, that is x power 2 plus any constant, such that the constant will be here in the vertex, right? And if we have it minus subtracted, this means that we have it starting from below the x-axis, where this value is the minus c. This is the x power 2 minus c. Okay, so these family of functions that exist all over the y-axis, their derivative is 2x. And to indicate this, we have to reserve a place for the constant, and this is what they do using that rule. Very well. Let's go further with the worksheet. Solving number J. No, I wanted number E. Here, of course, we have the integration of the cube root of x, which we can rewrite it as x to the power of 1 over 3. Also recall that x to the power of n raised to the mth radical is equivalent to x to the power of n over m, which is the power inside over the power outside, right? Minus, we have 1/2 here, We know that also from algebra, if we have a over b times c, this can be rewritten as a over b times 1 over c, right? We can do this separation for the terms in division and multiplication, so we can take that half away, and then we have 1 over the x to the power 1 over 3, right? All of this inside the integral, so I'll write the stretched s, the operator, and the dx. Now x to the power 1 over 3 is in the denominator. We need to put it up and move it to the numerator with reversing the sign of the power, because we want it to be ready for applying the rule, right? So we will say that now we can apply the rule directly. We have something minus something else. So we can apply the integration for that one first, and then for that one after that, separately. They are not related to each other, and we can deal with each of them alone. The minus act as separator, and the integration can be distributed. So we have minus, I can take the 1/2 outside as well, and then we have the integration of x to the power negative 1 over 3 dx. Now let's simply apply the rule which says that x is raised to the power of 1 over 3, we will add 1. 1 over 3 plus 1, we see it as 1 over 3 plus 3 over 3, because the 1 can be rewritten in terms of any number. So we have 3 in the denominator and 4 upwards. So we have here 4 over 3, and then divided the 4 over 3. Minus the 1/2 will drop, and x will be to the power, now take the negative 1 over 3, which is the power of x, and make it plus 1 in order to apply the rule, negative 1 over 3 plus 1, which can be rewritten as 3 over 3. And here it will be 2 over 3. So it will be x to the power of 2 over 3 over 2 over 3. And then don't forget plus c to consider any constant that were in the function, in the derivative. We are getting the function which have this under the integration as its derivative, right? Of course, we can rewrite this form in a more convenient form. If we have divided by 4 over 3, this is equivalent to 3 over 4 times x to the power 4 over 3. And then these two here can be simplified into 3, and x will be to the power of 2 over 3, and then plus c. So we'll have this as our final result. We can say that the result is capital I, denoting the integration, and this is the final result. Perfect. Let's move to another idea. If we have x power 2 minus 1, all is over the square root of x. Now we have x power 2 minus 1, and we have one denominator. We know that when we have a single denominator, this acts as a common denominator for the two terms up in the numerator. So we can divide them using the SOPs like that, right? And we can rewrite it as x to the power of 2 over the square root of x. Also, instead of writing square root of x, we can use its equivalent, x to the power of half, in order to make the two steps in one, and then minus 1 over the square root of x, which is x to the power of 1/2 dx. Now we did this separation because from algebra we know that if we have a minus b plus c, all of this is over d. This is equivalent to a over d minus b over d plus c over d. Right? So this is from a previous algebra. Now let's use another exponent algebra. If we have x to the power of n over x to the power of m, what do we do to the powers? Yes, we subtract them. So we can do this here, and we can say that this is equal to the integration of 1x, and the power will be 2 minus half, which is 3 over 2, minus 1 over x power. Yes, we can rewrite it as x to the power of negative half dx. Now we can apply the rule by distributing the integral into the two powers of x to have x power 3 over 2 That's the power plus 1. This one we can rewrite it as 2 over 2. So you will have 5 over 3. So we have here power 5 over 3 over 5 over 3. And then minus x power negative half. Again, negative half plus 1, which can be rewritten as 2 over 2. We take the number in the denominator. And then it's over 2. 2 minus 1 is 1. So it's 1 half. We will write 1 half over the 1 half. And don't forget plus c. We can rewrite this in a more convenient form by the 3 over 5, because 1 over 5 over 3 is equivalent to 3 over 5, right? These are equivalent forms, so we can rewrite 5 over 3 in the denominator. We can take it up, it will be 3 over 5 times or multiplied by x power 5 over 3 minus 2, also 1 over half is 2. 1 divided 1 half is equal to 2, as if it's 1 times the reciprocal, which is 2. So it's minus 2 and x to the power of half. One might write it as square root of x and it will be quite correct. Now we are done with that. Very well. This is another exercise from the worksheet as well. Let's think about it. We have x multiplied by 3 minus 4x squared all to the power of 2. Of course, this bracket of 2, we can remember it if we have x minus a all raised to the power of 2. We can expand this and we know that it's equivalent to x squared minus 2ax plus a squared, right? And if there were a plus here instead of the minus, this term was going to be the plus. So we can here get rid of that bracket which is raised to the power of 2, because we can't do this. We have x here times that bracket. We are not ready yet to apply the rule. In our way to apply the rule, or to get ready for applying the rule, we have to do that expansion. We know that 3 minus 4x squared all squared is equal to the first squared, which is 9, 2 times the first times the second. It will be minus 24x squared, and then the last squared, which is 16x to the power of 4. Let's put this here. I will just copy it. Now we have x times that bracket. Are we ready yet? No, there is an equivalent form to that form. We have to get x to the power of something and then plus something else. This product means that we need a product rule. Remember, in the differentiation as well, we had this. If there is a multiplication or division, we needed a special rule for that. But if there is an addition and subtraction, we can directly apply it. Now let's distribute the x to the other terms to have 9x and then minus the 24x squared times x, which will be 24x cubed, and then plus 16 x power 4 times x, it will be x power 5 dx. Yes, now we are ready to apply the rule. Let's apply it. The 9 is a constant, so it will drop. The integration of x is, we will add to the power 1. If it has no power, then it's 1. So we will add 1 and divide. Minus 24. X is raised to the power of 3. Let's update the power and divide with it. And then plus 16, the constant will drop. The updating the power of 5, it will become 6 over 6. And all of this, we will add then plus c. Let me tell you something before we get further. What about the integration of 1 over x dx? 1 over x dx is equivalent to the integration of x to the power of negative 1 dx. That one is directly the ln of the absolute of the x plus c. It's unlike the other powers, which means that if we have x to the power of n dx in the integral, this is going to be x to the power of n plus 1, like we did over n plus 1 plus c. This is correct, but for any n which is not equal to negative 1. If n is equal to negative 1 and only negative 1, and We don't mean here negative 0.9, negative 1.1, only exactly negative 1. Negative 1, when the x is in the power of negative 1, we don't add 1 and divide, but instead we say that it's the derivative of ln absolute x. Right? So let's go further with the problems and extend our talk to some more cases. So let's consider the derivative of a function now, not only a power of x, a simple power of x. Remember when we have 2 to the power x power 5 plus x to the power of 3, if we want to differentiate this, all raised to the power of 5, and we need to get the derivative. Of course, we know that the derivative to the power rule or the general power rule, we drop the power and then we subtract 1. And what's inside, we just copy it as it is in differentiating of the power. And then we continue by multiplying with the derivative of the function, where again we drop the power 5 times 2 and then we subtract 1. And then plus drop the 3 and subtract 1. So what happened here is that when we had a function raised to the power of n, the derivative of that function was as follows, was that we drop the power and we subtract 1 and we have the function as it is inside, and then we multiply it by the derivative of the function. So what we expect now, if we are reversing that operation, I need to take what was the result here, the n times the f of x to the power n minus 1 times the f dash. This should be equals to what? That's the derivative of this function, right? So if we apply the opposite operator of differentiation, which is the integration, like times 2 divide 2, like plus 3 minus 3, the derivative and the integration, they act the same way. So if we apply the integration to the result or the f dash, we will get the f of x to the power of n plus c. So what happened here to the power? Can we deduce the rule? Now let's deduce the rule where when we'll have a power of a function, not just x, but a function in x, like we will see, we will say that we have to have the derivative of that function beside in order to solve it and say that this function before the derivative was of the same power but plus 1 divided that power plus c. So we will take that old power and add 1, and then we divide with the new power. This will exactly be what we do. Let me take you to a simple exercise before we go to the worksheet problems. If we have inside the integration this bracket raised to the power of 5 multiplied by 2x, of course we will say that this product won't allow us to apply the rule because the rule needs a separator, which is a plus or minus. This product is not a separator. So we will think about the function inside the power and we will call it f. What is f now? It's x to the power of 2 minus 4. We will think about its derivative. What's the derivative of that x, of that f of x? It's directly 2x, right? Now, what from that derivative exists here? Oh, it seems that there is a derivative of the function beside that function which is raised to the power of 5. And this is exactly the rule that we discussed upwards. So if we have a function, we can write it in short, f to the power of 5 multiplied by the derivative of f under that operator. We can say that the integration can be solved directly as f to the power of 6 over 6 plus c. So this upwards will be the bracket as it is, raised to the new power over or divide that new power plus c, and that's it. What now if the derivative of the function here is not what we have exactly? What if there is a change? Let's see here part F. So in part F, we have the integration of the x minus 2, right? This is in a bracket, we can't separate it, and this bracket to the power of 5. This bracket to the power of 5, and we have the rule here, the bracket to the power of n upwards. So we have to take it up as a first step of simplifying it. We will take that power of 5 upwards with the opposite operation, with the opposite sign, negative 5. Now let's find out what we have here. We have a function raised to the power of 5. What's f dash of that function? It's better to write f and take it out of the power in order not to mess it up and differentiate it with the power as a general power rule. And it happens, by the way. If we get the derivative of x power 2 is what? Yes, it's 2x. And minus 4x, that's minus 4. And the 1 will go away in the derivative, right? So what we need here, beside that function raised to the power of negative 5, is its derivative. And we know now that the derivative is 2x minus 4. So we need to make this fit that. If you notice this function here, taking the 2 as a common factor, we will be left with x minus 2. What do we have here? This is what we have here already. But it missed that 2, right? So the mathematician said that if it's a constant that you miss, you can just plug it in. And then someone else said, no, we can't do that, because we are integrating the double of the function now, not the function that's required. And they get out of that trick by multiplying outside with a half. Now overall we multiplied by 2 over 2, which is 1. So 2 over 2, which is equal to 1. We rewrote it as 2 times 1 half. We took one inside and one outside. What we need inside and what we don't need, we leave it outside. And with this, now the balance is correct and we can apply the rule. We can apply the rule that we have discussed upwards. That was the rule. Now we have the f dash and we have the function to the power. If the derivative is ready, then we are ready as well to solve and apply the rule. The half, which is extra, will come and drop. And now we have f dash as this whole part. The 2 times x minus 2, all of this is the derivative. So it will go with the integration simple. And what will drop, like we know here, is the function with its new power divided the new power. So x power 2 minus 4x minus 1 will drop. And the new power is what? Negative 5 plus 1 is negative 4. And don't forget to divide by 4. So we will say divide by negative 4. And then plus c. That's it. This is the integration. Let's go with number g. We had another problem like number g, but the power in the bracket was 2. And of course, we are able to expand the power of 2 when we have it in the bracket. But what about that power here? That power is 10, which we can't expand it. We don't have an expansion for it unless we multiply this bracket 10 times with itself, which is very time consuming and effort consuming and everything. So of course, we will think about it like the general rule of the integration. So we think of what inside the power here as f, raised to the power of 10. What is left here is f dash. What's f? F is what's inside the power, right? What about f dash? That's 4x. Oh, what's here? Do we have beside the function from that derivative? We have the x, but we are missing the 4, and we can add the 4 inside and add 1 over 4 outside. to have 1 over 4, and then we have 4x, which is the derivative, and the 2x squared plus 3, which is the function, power 10. Now we have, yes, a function power 10 and times or multiplied by the derivative of the function. This integration can be solved directly, like the 1/4 will drop, and we can apply now the integration rule, which says take the bracket as it is and update the power, divide by the new power. Don't forget plus c. What is only coming from the exercise is what's inside the bracket. But as you see here, the f dash goes with the symbol of the integration and the dx with the f dash. And this bracket drops with its new power divided the new power. Very well. Let's get a different exercise. Here we have 1 minus 2x, and it's not squared or to the power of 10. No, all of it's to the power of the square root. This is of no problem. We know that the square root is equivalent to the power of half. So we can rewrite this into the power of half dx. And now we have a function which is inside the power, and we need its derivative. What's the derivative of this function? Yes, that's minus 2. So we have now this bracket raised to the power of half dx, and what's left is the derivative that we need to solve the integration. So we can add it here and cancel it up outside. So this is going to be equal to the negative 1/2, which is extra here. It will drop, and we are able to solve this integration. We will get the bracket with the new power, which is plus 1, and divide by that plus 1, and inside we have 1 minus 2x. Don't forget to add the c. Of course, this can be simplified out to be negative 1 over 3, and then this 1 minus 2x will be raised to the power of 3 over 2 plus c. Right? That's very well. Now in number I, we have x power 2 and then 3x power 3 plus 7 raised to the third root, or the cube root. Of course, we need to get rid of that root, right? The radicals doesn't exist in our rules, so we always need to get rid of it. X to the power of 2 is okay, we would accept it. And then 3x to the power of 3 is fine as well. And then plus 7 is fine, and we will move this cube radical into power 1 over 3. Very well. Now we can see this as a function that has the power 1 over 3. It's unresolvable, and we are searching and looking for its derivative. If f is what's inside the bracket, it's that form. What's its f dash? We will drop that 3, and then we will have 9x squared. What we have will always be the x part, and the constant can be there or not, because if it's not there, we can just add it and then cancel it outside, right? Now we are ready to solve. Yes. Now we have the rule. Yes. We have a function raised to the power of 1 over 3, any power, and then times the derivative of that function. So we can say that this integral is equal to the 1 over 9, which is outside, the extra will drop, and what will drop from the integration and all that's inside is only the bracket with the new power. 1 over 3, let's add 1, which is 3 over 3. This is going to be 4 over 3. So the new power here is 4 over 3 divided by 4 over 3, and don't forget plus c. What's inside will drop as it is without any change. Okay? Okay, now what about part J? Let's move to part J. We have inside the integration 1 plus the square root of x, all raised to the power of 3, and then we have x to the power of half in the denominator. Can we take it upwards and also rewrite the square root as half and take it outside upwards to be negative half, so we can write this as x to the power of negative half dx. Okay, now it starts to reveal as f raised to the power of 3, and we need to make sure that that's f dash. So if f is what's inside the bracket, what's f dash? Yes, f dash is the derivative. Derivative of 1 is 0. Derivative of root x is half x to the power of negative half. What's left from the derivative here? So what we have here is x to the power of negative half, and the half is missing, so we can add it. We can say that we will add the 1/2 which we need here, and we will cancel it upwards. What we see now is we have 2 times and the integration. 2 is the coefficient of the integration of that function, and then we have the half times x to the power of negative half dx. What is that now? This is a function raised to the power of 3, and this is the derivative of the function. And we have the 2 outside and the integral. So we can say that directly that's 2, and the integration of all of this is only the f raised to the new power updated to 4 divided by 4 plus c. What's inside will be exactly as it is, 1 plus the square root of x without any change. Very well. Let's have a look over some word problems. So we have here a company produces a product for which the marginal cost of producing X units is the marginal cost, and then it's written as dC by dx. It seems that that's the derivative of the cost, right, which is given by 2x minus 12. And the fixed cost is the $125. We need to find the total cost function and the average cost function and the total cost of producing 50 units. Let's start. Now the company now let's take the marginal. If we have the dC by dx, and in part A we are required, in part I, we are required to find the total cost C. We need to know C is what, and we are given dC by dx. What is the operator we have to do and apply over the dC by dx in order to obtain the C without a derivative? If it was multiplied by 2, we know that we divide by 2. If it was plus 4, we know that we will subtract 4 to cancel it. Now, if it is the derivative, we will apply this operator to get rid of it in order to obtain the C. And here we go. We will add the function inside and then apply the rules. 2x minus 12, minus is the separator, so we can integrate 2x by itself. 2 is a number which drops, and x will be power of 2 over 2. Minus 12, which is a number, that was the derivative of 12x, right? This was the first rule that we mentioned in that slides. And then we don't forget plus c. And let's call it here k in order to differentiate between it and the cost, the c for the cost. So this is the C now, the cost, right? We know that the total cost is equal to the marginal cost or the varying cost plus what? Plus the fixed, right? So this part at the end would represent the fixed cost. And that part which varies in x is the marginal. We can call it the varying as well, the varying cost. So we can say that we are given here the fixed cost, by the way, directly, and the fixed cost is 125. So we know directly that the total cost is the we can take out that 2 with that one, right? And drop the x squared, and then minus 12x and plus the fixed cost, which is 125. And here we go with the total cost. Very well. Now we need to find the average cost. Of course, we do remember that the average cost was the I bar. The C bar. And the C bar is the total cost divided by X. The total cost that we got in part I, which is like that, we will divide it by X, where we divide each term by X. This is a common denominator, remember? So we can simplify each. Minus 12 and then plus 125 over X. So this is the average cost required for double I. Okay, what about the triple I? In the triple I, we need to find the total cost of producing 50 units. That was the total cost, right? That we got in part I. We need to know the cost for X equals 5. It can say for producing 50 units, and we understand that this is denoting the X, or for production level of 50, right? So it can be said in any way. We can say that the required cost is the same cost that we got in general, and when the X is 50. Let's take that final solution from the solution of the worksheet. So it's 2025. That's the cost for producing 50 units. And then we have another word problem. Suppose the marginal profit for producing X units of a product is given by that function. That's the marginal profit. We know that the word marginal denotes a derivative, and also it's given as d by dx. So it's very obvious that it is the derivative, right? So what we will do is that we will get the profit. We are required here to find the profit, which is the capital P, assuming that selling no items results in a loss of 400,000. Now first, let's think about the profit. This capital P represents the profit as usual in thousands of dollars. And what we are given is the dP by dx. Can we know what's the P from that given? Yes, we know that we apply the opposite operator, which is the integration with respect to dx. So we will integrate that function that we are given, and then minus 3x, and then plus 150. Okay. Now we have in between these functions minus and plus. So this act as separators, and we can do each alone. So let's integrate the x to the power of 2. And what about the 25? It will drop, and it will drop in its place. If it didn't have a place here, we can multiply it by the 3 in the denominator, or just put it outside like that. Minus 3 and x will be squared over 2, and then plus 150, we will just attach the x. So as if we're integrating every term alone, and don't forget plus c, right? Now the second part of this problem is to be able to find the full profit formula, where find the profit function. We have already done this, assuming that selling no items. No items means that the number of items is what? 0. In a loss of 400,000, and this selling of no items results in a negative profit, because it says a loss. So loss is a negative always, negative of this $400,000. So now we know that the profit of 0 items is equal to the 400,000 with the negative sign. The P of 0, okay, we can substitute the x here by 0, right? And then instead of 0, instead of x, we substitute the x by 0. And then we are left with one constant, which we call it k here. So here we are left with one constant. Of course, anything times 0 goes, all these times 0 goes, and then we can know that k is equal to the negative 400,000, and therefore the total profit can be rewritten as the 1 over 25 and the x power 3 over 3, the same formula as it is, minus 3 over 2x squared plus 150x, and now it's minus 400,000. That's the full profit problem. Now we have went through the basic integration rules where we have x to the power of n, we add to the power 1 and divide. This happens if the power is not negative 1. However, if the power is negative 1, like it's indicated here, we change this into the len of the absolute of x, and in the next time we will see the exponential integration. And I would like at the end of this part to thank you for your attention. See you.